The previous videos covered how is the Dirac Delta function covered in basic undergraduate engineering textbooks. And we said they all covered kind of shallowly. They kind of define what it is. And it's a limit of a function that integrates to one. It's zero everywhere except at the impulse, yada, yada. But it's treated like a function, even though they admit it's not a proper function. And why isn't it? Why isn't it a proper function? Function, find a good old elementary calculus course, maps real numbers to real numbers. Infinity, not a real number. That's why they use curve parentheses, right? The limit from minus infinity to infinity, because the real line doesn't actually include infinity, because it's not a real number. But you say, but things like 1 over t goes off to infinity. And yeah, infinity is not a real number, but at the impulse, the Dirac delta function is infinity or something like it. You say, well, why is it 1 over t or the natural log of t? They're legitimate functions, right? But 1 over t blows up at 0. It goes off to infinity. Natural log is undefined for anything 0 or less. It's not a positive argument. Functions are defined on a domain. They map real numbers to real numbers, but actually a subset of real numbers. So 1 over t, the domain of 1 over t is all real numbers except 0. You know, here's that function, and they just say, well, it's not defined at 0. And you can take integrals over that, and it works out okay. Just exclude that in the domain. You can't exclude it in the Dirac delta functions domain. Then you lose this key property that it integrates to 1. So we're kind of stuck. We have to include 0 in the domain. And it's not a proper function. So that's why it's not a proper function. So how should we go about even coming up with it and deriving properties of it? And I'm going to describe these 3 basic approaches. The first one is basically like, I think Paul Dirac did. Actually, I'm not sure he defined it as a limit of a function that integrates to 1. But he ultimately come up, it had 2 key properties. It integrates to 1 if the integral rattles 0, or where you place the impulse. And then it's 0 everywhere else. So you just start with those 2 properties. And we can visualize it as a limit of a function. I'll talk about that in a minute. And the second approach is distribution theory, generalized functions. This is the one that is mathematically rigorous. And I'm not going to say I know a lot about it. I'll talk about it a little bit in later videos. But this is the deep math stuff. And it might be mentioned in an undergraduate textbook, engineering textbook, but it's not really dug into. They don't derive things very much at all. It's just like, oh, here, by the way, it's all based on this theory that we're not going to explain. A third approach, which I think I see in some places, instead of starting with this, it's a function that integrates to 1, you start with the sifting problem. You define that as a defining property of the Dirac delta function. And then do kind of like this first approach, you still treat it as a function and pretend normal calculus works. And through this series of videos, I'll cover all these to some extent. There's drawbacks to each. There's things I really irritate me about some of them. And I'll get into all those in subsequent videos. We'll start finally getting to the meat of this in the next video.